Good morning, everyone. Just now in Professor Sun's talk, he discussed about how to measure a particular product. Whether a product is good or not mainly depends on whether users find it useful, right? And just now, Dean Yu was also discussing the importance of data for our manufacturing. Actually, I especially want to thank Dean Yu here. Do you still remember when IoTDB was first released? It was in February of 2017 at the China Industrial Internet Conference, where it was officially released for the very first time as a crucial part of our independent innovation efforts. Here my topic is specifically called The Leap from Data Collection to Comprehensive Data Utilization in the AI Era. Actually, there should be a very important question mark at the end. How do we truly make the crucial leap from data collection to effective data utilization in this AI era? How can we effectively achieve this significant leap? I think this is indeed the most important core issue of our entire conference. I'll start things off and set the stage for our discussion, and then we'll listen to everyone's valuable thoughts on how to effectively move from data collection to comprehensive data utilization and how to make truly good and efficient use of it. So when making this particular presentation, I kept pondering over it quite deeply. I started my graduate studies with the esteemed Professor Sun in 1990. So it's been exactly 35 full years now since then. During this significant period, Professor Sun diligently led us and helped us successfully secure the prestigious National Engineering Research Center. Professor Du is our esteemed collaborator, not just a collaborator actually. Back in the year 2000, I was actively working with Professor Du under the distinguished leadership of Professor Sun on the crucial development of comprehensive databases for major national projects. In fact, time flies. Just like that, it's been 20 years or even 10 years in the blink of an eye. Recently, people have been saying we've entered the AI era. There have been several changes, and especially for us in the software industry, these changes and impacts are particularly significant. Just a couple of days ago, one of the founding members of OpenAI, who was also Tesla's former head of AI, talked about the 3 stages of software development: software 1.0, software 2.0, and software 3.0. So what is 1.0? It's when we started from assembly language, right? Back in the days, Mr. Zhang Kechang was also a programmer. We evolved from assembly to high-level languages, and we've kept developing up to now, right? We've developed so many languages like C, Java, Python, and so on, right? Actually, all of these still fall within the scope of 1.0. At that time, it was up to us programmers to write algorithms and organize the code. As for 2.0, that's what we refer to as the current era of large models, right? These models are trained by feeding them data, then parameterizing them, and after that they have an inference engine, right? Everyone knows about the popular VLMs nowadays, right? They're basically like operating systems now. You just input something and it gives you the answer. All the interactions and everything else are generated automatically. So its parameters are essentially data, and the model itself becomes a massive piece of software, right? Now, what is software 3.0? It's about using prompts with large models to write software, right? I imagine many of you here have already tried it, maybe even built something fun or surprising. It's already become very widespread, so why do I think this diagram is well drawn? It's not that one stage replaces another, rather these 3 stages coexist. There will always be some people working on 1.0 tasks, some, though fewer, working on 2.0 tasks, and others working on 3.0 tasks. In this way, the software ecosystem is greatly expanded. In other words, everyone becomes a programmer, right? Everyone becomes a creator. This is now a reality. So now, just yesterday, Tsinghua University also held a meeting emphasizing that empowering all disciplines with AI should be made a top priority. Some people, like academician Joji, have said that AI is a technological revolution, while intelligent manufacturing is an industrial revolution. I think there is some logic to this perspective as well. The second thing is, if we take another look at the field of computer science, actually after the emergence of AI, its impact on computer science has been comprehensive. This happened around April of this year, specifically during the windy season. Tsinghua University held a high-level academic forum on computer science, and a distinguished professor from MIT presented a compelling diagram that I found quite thought-provoking and insightful. At the very least, it truly represents a particular perspective, this specific perspective. So, where exactly is AI situated, and where does traditional computer science precisely stand? So we can see the core device architecture, and the system itself has basically remained unchanged, though of course there have been some changes. So what exactly has changed? We used to rely more heavily on CPUs, but now we primarily use GPUs, correct? Previously we operated on single process operating systems, but now we're on parallel clustered operating systems. There might be a shift, but the core still exists. However, what do we see being heavily impacted? It's a new overlay layer above the application. All right, when it comes to AI, everyone has their own perspective. I'll just use these two slides to give you a brief overview. Second, what developments have there been in industry? Right, industry. Today we're talking about empowering the manufacturing sector, empowering industry. I've been using this slide for many years now. Recently, Professor Long told me that we need to draw a new one. Indeed, it's time to evolve, but the core logic hasn't changed. That is to say, in intelligent manufacturing, one thing happens at the edge. The terminal devices will have computing power and communication capabilities, right? Today, Feng Tan is here with us. For our work on the C919, most of the systems on the plane are still wired, most are card-based. So, for an intelligent connected device, like what Ms. Wang Yan is doing here with energy storage, there are also significant changes happening at the edge. And after these changes, there will be fundamental transformations in the ecosystem and business that follow. So what does true cross-industry integration look like? It happens after the changes at the edge, a complete restructuring, a reconfiguration that merges the primary, secondary, and tertiary industries all together. All right, so let's get back to today's main topic. Today we're talking about data collection, so I'll move through this quickly. Since the 1990s, I've been working with Professor Sun on CAD, which falls under enterprise informatization in the upper left corner. In fact, this actually started even before the 1990s, right? The second thing is our various products, as I just mentioned. Intelligent connectivity. The third is internet data. These particular types of data are actually quite familiar to everyone today and are used very frequently. I just want to remind everyone that these are all essential elements we work with. They are indeed our main components. So today, when we look at industrial time series data, back then it was called industrial big data. In 2012, GE was already discussing what industrial big data is. The title they used was quite grand. Industry big data, right? But what they talked about underneath was large-scale time series datasets. And what does that refer to? It refers to data generated by equipment. So there are many conclusions and scenarios discussed here, but I won't go into detail. The second point is about high-value data for enterprises. Even today, high-value data remains an important means for us to manage and utilize within companies. At that time, Professor Sun led everyone in working on the informatization blueprint, right? At that time, we were already talking about the concept of 30% technology, 70% management, and 120% data. Even today, we can still see this on the client side and customer terminals. This slide is actually a diagram drawn by Boeing in the early 1990s. You can see it illustrates two things. First, that data at the center is the core of all manufacturing, a single product data source. And then, processes fundamentally revolve around essential data. This crucial data truly empowers and effectively supports all related processes. So I think this logic is still relevant today. Moving forward, there's a massive amount of data from things like climate, environment, policies, and so on, right? All right, so looking at today, in addition to traditional informatization, there's also a significant and evolving trend of IT and OT convergence. What exactly has all of this accumulated for us, and what are the broader implications? We've accumulated data. Judging from today's topic up to now, what we've been talking about is still about data collection, collecting data. So, how do we actually utilize the data? Just now, we saw that points 1, 2, and 3, they are about the sources of data. That's the process of collecting data. Of course, during the data collection process, we also use data. For example, when we're collecting, we might have alerts and monitoring, right? In information systems, we have querying and searching, and in meteorology, we do some data integration. This is what we call the digitalization of industries, industrial digitalization. Now, pay close attention. This year, I've added a dashed line right here. What exactly does this dashed line truly mean? It means that now, data absolutely needs to be fed back to effectively control our equipment to create a truly closed-loop system. This is a new level in data utilization, whether you're just able to simply view the data or whether after viewing the data, you can use it to optimize your industrial systems and even achieve full automation through this closed loop. This clearly represents a significant step up. Another aspect is the 2 stages of data usage: business intelligence, BI, and artificial intelligence, AI. This stage is also referred to as digital industrialization. So the core issue, and what I want to focus on today, is these latter 2 stages. We need to do a good job with digital industrialization and truly empower our business systems with digital technology. That's why today, the main purpose of my report is to raise questions about this matter. In fact, I don't have the answers myself, and our team is also exploring this issue. How can we truly achieve digital industrialization? We just have some of our own thoughts on this. So, this diagram here, actually, everyone has been using it repeatedly. After 2 full years of dedicated practice, we genuinely feel that diligently following Professor Du's profound concept of the 3 essential circles, right? There are matters of software, matters of the domain, and matters of mathematics, ABC. Now, looking at it more closely, its overall success rate is truly the product of these 3 crucial factors, not merely their simple sum. In other words, whenever we perform exceptionally well, it's always because we have truly good clients, isn't that right? We also have incredibly capable colleagues and wonderful friends from within the domain, including all of those esteemed individuals present here, wouldn't you agree? On top of that, we also have our comprehensive software tools, plus some advanced mathematical methods. Otherwise, our overall success rate would be almost entirely 0. It's never truly the case that just having a good tool alone can completely solve all of our complex domain problems. The second thing is, everyone always says this is the crisp DM model. When we use data to solve problems, we follow 6 steps, right? It's like the old joke about putting an elephant in the fridge. We start with business understanding, then data understanding, data preparation, building the model, model evaluation, and finally implementing the solution. After doing this for 5 or 10 years, with Professor Sun leading us, he kept reminding us, you haven't reached enough users, and the deployment results aren't convincing yet. Everyone is working hard, but if we think about this methodology, what do we usually do? We usually start by getting a data set and begin from the second step, data understanding. Then we move on to data preparation, tuning the model, and then proceed to validation. In fact, what we mainly did was the work on the right side. We spent a lot of effort on that, and the company also invested a lot of time for us. But when it comes time to actually deploy and use it, we often face significant challenges. Now, what we truly want to do is change our fundamental approach and put practical usage first. That is, you absolutely need to ask yourself this crucial question. If this particular problem can be effectively solved with available data, then precisely how do you close the loop and seamlessly integrate it into your existing workflow? First, think this through, then consider the business aspects, and only after that, focus on the data. Essentially, start with the end in mind. I think this is our fundamental idea. All right, so next I'll quickly talk about today's topic, okay? Xiangdong and Jialin have been pushing things forward, so now we've reached the stage of actually using data. At this point, IoTDB is no longer just a database. It must incorporate AI-INDB to create a closed loop, and it must also bring the terminal, the IoT node, into this closed loop. So, as I mentioned earlier, there's a downstream process, but if there's no carrier, it can't go downstream either. So, for this lower line, we specifically take the TIS file, then convert it into a comprehensive CSV format, and subsequently make it readily available, truly accumulating valuable data sets. So where do we actually put these data sets into practice? The first example is at Chengfei. They use it for the entire manufacturing process. In the words of their director Sui, "I don't care about the application system, but the underlying data must be stored in this format." Now, looking at their data set, which exceeds the petabyte level, it's already very useful. People often say transferring data is easy, but who's actually going to do it? And what if there are issues after the transfer? That's very difficult. But if you store it in this format from the very beginning, then this problem is solved once and for all. So today, when we talk about data lakes, the core idea is to decouple storage and compute workloads, to break them apart. All right, so within this big framework, we want to use AI, something everyone is working on, right? Using prompts, we can directly process time series data, right? Now, it's also registered on MCP and has been added to the official website. The second thing I want to talk about is data quality. When Professor Long and his team were working on those meteorological models, they repeatedly proved that data quality is just as important as algorithms. Once the algorithm is set, it's the data that determines how good your model can be. This is something everyone really needs to invest effort in. Recently, we've been working on this. Professor Long and his team have been working on a data set with 1 trillion data points on a single node. For this volume of data at a single node, we keep working on it over and over. And even now, issues like time alignment and missing values still exist. They're still there. The second point is why Professor Long will share about large models later today. It's because in reality, we've collected a huge amount of data, but most of it is just lying dormant on our hard drives. We did some statistics, and it turns out that approximately 80% of people who are using IoTDB are only querying recent data. Very few are looking up older historical data. What does this mean for us? It means that a lot of the older data is just lying dormant. Nobody is using it. So now, how can we leverage large models? If you look at the scaling laws of large models, you'll see that having a larger scale brings significant benefits to the quality of the model. And if we look at, for example, massive wind farms like Goldwind, they have huge amounts of historical wind data. We also need a way to properly activate and make use of that data. Finally, with large models, AI in DB, we can actually use SQL to perform post-training on models. In other words, in the future, everyone can be a data analyst. As long as you truly know how to use IoTDB, you can train models, do traditional data analysis, and even fine-tune large models with great precision. And of course, once this is done, it will feed back into the inference process, creating a closed loop. This is an example of predicting transformer oil temperature. So now, if we carefully look at the biggest change from business intelligence BI to artificial intelligence AI, it's that BI primarily analyzes past events, while AI is fundamentally about predicting what will happen in the future. As a result, all kinds of predictive controls and predictive decision-making are being integrated into our various business systems. Finally, I'd like to use this particular slide to talk about a very important scenario, which represents a fundamental and deeply held belief of ours, that all terminals, without exception, will become increasingly intelligent over time. No matter if it's massive airplanes, colossal ships, or incredibly high-speed trains, these sophisticated terminals will definitely possess more and more advanced computing power. There's another crucial thing to consider, right? That is, the cloud is not just about aggregation. It's essential to refine these models and knowledge in the cloud and then push them down to the terminals. So in the end, what will this lead to? It will truly create a cluster of clusters, a world where humans and machines thrive together. Looking ahead, today we've extensively talked about large time series models, but in the foreseeable future, world-scale models, or more precisely, spatio-temporal large models, will definitely have even more significant room to grow and expand within the industrial sector. That concludes my presentation for today. Thank you all.